Hello everyone, my name is Syed Ghazanfar Abbas and my project title is Selection of Intrusion Detection System Security Policy. The following elements are included in the finalized project proposal as a result of the guidance and support of Professor Chennai Peng. These items will be discussed in this presentation in detail. I shall start with the fundamental concepts that are very relevant to this presentation and project. Then I did two implementations in this project. In the first implementation, I enhanced an existing open source IDS by adding an IoT protocol implementation that is not available so far date in it. In the second implementation, a Python script that automatically developed the IoT security policies using the PCAP files of an IoT use case. And finally, I tested my implementation and the policies using an open source IoT penetration testing tool in which the different attacks are already implemented. The internet has been around for a while and it has a lot of information about people. In traditional internet, all of the data, recordings, schemes, books, trade, and so on are all made by, for, and about humans. With Internet of Things, things begin to share their experiences with one another. This is how it works. We take the things and add the ability to sense and communicate. One of the serious concerns that arises with IoT is the security. It is a well-known fact that the majority of the IoT devices will be supported by sensing and actuating devices, which have limits on their capacity of computing power, energy, and memory. The incorporation of such devices into the Internet communication infrastructure will enable end-to-end communications with other devices everywhere on the Internet, but will also open up new attack vectors from such less constant hosts. For example, Mirai is one of the famous IoT attacks. This slide shows an increase in the IoT attacks in the recent years. Protocols have influenced the security debate and thereby opening up new avenues for discussion. Considering the well-known and extensively used protocols that are not adequate for the significant advancement of IoT, new protocols that may match the light devices used for communications have been introduced. As a result of their recent existence, security is a crucial research topic. Therefore, we begin by analyzing security in the context of the Internet integrated sensor networks, more precisely how intrusion detection may be applied to IoT QAP communication environments is our goal. The QAP is an application layer IoT protocol. Nowadays, many vendors actually using the QAP for their IoT devices since it is a lightweight and consumes little energy. QAP primary function is to behave similarly to the HTTP whenever the constant devices are involved in the communication. It bridges the HTTP gap, allowing devices like actuators, sensors to communicate over the internet. QAP is by default connected to the UDP and optionally DTLS, offering a high level of communication security. After looking at IoT and the serious security concerns in IoT, now let's see what we have in the traditional networks. A heavyweight security solution is an internet intrusion detection system. So it's basically a hardware or software program that monitors a network for the malicious activity or policy breaches and is known as intrusion detection system IDS. While reading about IDS, a key question comes in mind: what's the difference between a firewall and the IDS? So mainly the firewall is a device or software that examines packet headers and applies policies depending on the protocol type: source address, source port, or destination port. But an IDS is a device and application that examines whole packets, both header and content, for the known occurrences. Nowadays, there are many widely adopted open source IDS. Some common are prominent are Suricata and Snort. In this project, we will consider the Suricata IDS, and the main reason of it is that it is the first IDS that actually adopted the multi-threading feature in it, it's considering for its performance. So that's why it is widely adopted in the security community. So now I will explain about the first implementation in which I enhance Suricata with the QAP implementation support, meaning that now it can provide defense against the QAP application layer attacks. So the documentation that is considered technical document in which I have put the code snippets and it explain that what are the changes done in the existing Suricata and how these changes will be effective. And also a video is published on the YouTube where I have run the complete setup of installation of the Suricata with the enabled QAP and made a little test with on a pcap file using it. To date, it's not just the Suricata lack the support of the QAP, but also there is no open source IDS as per my understanding that actually support the QAP protocol. So recently Suricata has actually introduced one of the IoT protocol that is MQTT. So suddenly when this protocol is introduced, we see a lot of commercial and open source security policies for the MQTT. So this lead to the conclusion that if MQTT is introduced in traditional internet security solution, then QAP is also one of the candidate to be added so that it can secure not only the traditional but can also be utilized in the IoT framework. So with the lack of the QAP support, obviously two things that are prominent here is that one is that IoT applications that are using the QAP are vulnerable to attacks, and we can see certain attacks that actually having on the application layer of the QAP. So the second is that the lack of security policies for QAP. So one of the top security policies provider emerging threat. It doesn't have any security related to the QAP. I believe this is mainly there is no QAP implementation in the IDS, so they are not working on it. There are two key challenges that actually happens to me when we start working on this project. One is there is no formal explicit documentation guidance for adding the new protocols. So mostly the protocols are added by the uh, IDS providers themselves. So that's why there is no specifications, a technical document specification that can help to add new protocols. Secondly, it's because Suricata is a multi-threaded intrusion detection system, so it's really hard to debug and understand that how it is actually working. So to counter the challenges, we actually started with the understanding of the existing protocol implementations. One is HTTP, another is DNS. HTTP is obviously a TCP base, and DNS is a UDP base. So we understand that how actually the Suricata work on the existing protocols. And based on the understanding, we devise a high-level architecture that is also very relevant to the majority of other open source intrusion detection systems that actually can give guidance that what can be considered in the other IDS if they need to be extended for the protocols. We divide our protocol implementation approach into four steps. In the first step, we will identify the protocol, the packets are whether QAP or not, and in the second step, based on the RFC of the QAP, we fill parts of packet and data. And in the third step, we will identify the keywords that are relevant to the information in the packet and that can be used in the rules. In the fourth step, because a new protocol is embedding in the Suricata, so it need to be consistent with the existing functionalities. For example, there are some functionalities that are not protocol specific. So when a new protocol is integrated in such IDS, those functionalities should be automatically affiliated with the infrastructure if it is implemented properly. For the protocol identification, Suricata by default uses two approaches. One is the port-based identification, and another is a packet type pattern-based identification. In port-based identification, a default port is specified, so any traffic coming on this port, Suricata consider it as a respective protocol traffic. While in the packet type pattern-based identification, we specified certain patterns that the Suricata try to find in the packet. If it is not coming to some default port, then it is considered as a relevant uh, protocol packet if the patterns are matched. Once a web protocol is identified, the next step is to parse a packet according to the packet type. So for each packet type, there is a parts document, part file that is added in the Suricata, and based on that, once a packet type is identified, then we look for the bytes according to the protocol specification, and finally we parse a packet and fill the variables with the data that is available in the packets. Once the parts packet data is filled in the Suricata variables, then there are certain meaningful variables are defined which are considered as the detection variables. These variables are filled with the data that is already parsed in the previous stage, and now these variables are available in the rules and or the policies. More technical detail about this process is mentioned in the technical report as well as in the code comments, and that is uploaded on the GitHub. An important step for adding any new protocol in the Suricata is this, that it must be accommodated with the existing infrastructure. For example, adding a new protocol requires protocol specific modifications, for example, the packet parsing based on the protocol specifications, protocol detection, etc. However, there are some generic features that are already supported by for all new protocol if they are correctly integrated in the Suricata. For example, memory allocation, deallocation, generic keywords for the detection. At a high level, we have modified some of the existing Suricata file to configure out the QAP support, but mostly the new files are added. So this slide shows some of the changes that we have done to the new and added new files. For more detail, please consider the technical document and the code comments. Till now, we have extended the Suricata with the QAP implementation. So now the goal is to create the policies that we can use in the Suricata and test our work. So we create a Python script that in the passive mode iterate the pcap file, that is actually the IoT use case traffic that we have captured, and then it actually, so any traffic whenever given to this script, it analyzes this traffic and generate the certain security policies. The script is available at the GitHub location. Tool generation application generates device profile from the pcap file to detect anomalies. A network anomaly is a divergence from its predicted behavior, which is described by a profile based on the network activity. For example, we run this application on a pcap file and we found the certain rules as shown below. In these rules, it is clearly depicted that for each packet type, we found that the number of traffic packets coming to a web server are limited, and we have made a check here that if within a duration, so if the packets more than the certain number of packets will appear, then this is considered an anomaly, and this anomaly will be reported by the system. Slide shows that the Suricata is not able to detect the web traffic and also generate the alerts when the security policies of the web are violated during the traffic. With our two implementations, now we can test them on an IoT use case with and without the security policies. The complete testing process is shown in a YouTube video. The link is shown on the slides, and also the three VMs that are used in this testing that are developed by me are also uploaded for anyone to use. We have used tool PenIoT, penetration testing tool for IoT for testing. It is an open source tool which has already developed certain attacks for respective protocols. The slide shows that it supports a QoA protocol in an MQTT and respective IoT protocols. This is our testing topology. Three VMs that are run. One is QoA server, other is QoA client, and one is the attacker. Suricata that is enabled with QoA is running as in an inline mode. All the traffic coming from or to the QoA server is passing through the Suricata. The right side screenshot shows the video screenshot that shows the three VMs. So the first we run the QoA server as shown in the screenshot. Then we run the QoA client. The commands are shown in the screenshot above. Then we run the attack penetration testing tool, PenIoT. The left side of the screenshot shows the type of the attacks that it is providing. The left side of the screenshot shows that the PenIoT, the testing tool, is able to do the attack on the web server, but the right side shows that the attack is stopped due to the security policies that are embedded in the Suricata web. In this project, we enhance an open source IDS with the QAP protocol support, which make an IDS to be used as a defense for the QAP against the QAP attacks. This project can also help in developing the QAP security policies both openly and at the commercial level. Finally, I have put all the videos that will actually demonstrate that how to implement such stuff and how to test it publicly available. The codes and the other relevant information is also publicly available.